Another topic of Chapter 5 is curve fitting. So we can create a data and create more data. And I can do a plot. So plot away, and I get this kind of thing, and I can change my plot. Let's go property editor, and I'm going to open plotting tools, etc., etc. It's doing its thing. It's doing its thing. Click on this, and I can do. I can put in a marker, circle marker, so where my data is, I've got a circle now. I can also do and I forgot tools. There's tools. Okay. Tools way down here. You can do basic fit, data statistics, means, medians, stuff like that. Basic fitting though, it pulls up a window. So if you want to fit data, here's your figure window. Go to the tools, basic fitting, tools, basic fitting, and you'll get this window going up. So you could, for example, pick a linear. You could show the equations, plot residuals, and so forth. In fact, that's exactly what it did here. Okay, I've got too much crap going on. I can get rid of the plot residuals. You can choose how to plot. Oh, wait a minute. I was trying to get rid of plotting residuals. It went away. You can choose how to plot residuals also. Let's see. You could put it in a separate figure. Instead of one on top of the other, you could put it in a separate figure and so forth. You can have a quadratic fit. You can see how, and I'm showing equations. I'm going to choose both linear and quadratic. And let's see how they both work. So linear does this. Quadratic looks more like that. I'm wondering about it. Let's see. Show equations. I'm going to show the norm of the residuals, and it doesn't tell me where it's at. So the quadratic equation, the residuals are in teal. Residuals are basically how far away are you. So the mean residual is 11.1 or 11.2 if you have a linear fit. So the deviation from your data, that's what residuals tell you, is how far away are you. Looks like the quadratic is a lot better. Cubic doesn't look a lot better than quadratic. Take a look. Purple bars are cubic, green bars are quadratic. So you make a big jump going from linear to quadratic, but going from quadratic to cubic, not that big a jump. So you might think your data is closer to a quadratic fit is probably best for your data. Okay, so that's curve fitting. I'm not going to show interpolation. You can also interpolate. I'll let you read that in the book. There's a lot more to statistics. I'll let you read that in the book. Okay. Moving on. So a lot of book reading. Numeric integration. It's called quad. When we get to symbolic, integration is INT for integrate. Differentiate is DIFF for differentiate. But numeric integration is called quad because it's the particular algorithm that they use, quadrature numeric integration, which you may have seen in Calculus 1 or 2. So quad, QUAD of an expression, exp to the x. And let's see, that, and I don't want the, there we go, get rid of that. And I think, no, I do need the parentheses, I do need the single quotes. There we go. Limits 0 to, or excuse me, 0 to 1, 0 comma 1. So this is just the exponential function. The integration of the exponential is the exponential from 0 to 1. So we ought to get Euler's number out. We don't. I wonder what the problem is. Let's see. E to the 0 is 1. So I should have gone negative infinity. Infinity is a reserved word in MATLAB, by the way. So it ought to be able to handle this. Oops, doesn't like it. Okay, I've got to use real numbers. Negative 1,000. There we go. It should be real close to Euler's number. And I thought it would pick out negative infinity. You could program it to do negative infinity if you wanted to. This is where you could create your own function so that if it reads infinity, it would say, oh, okay, well, e to the negative infinity is 0. So I know that the value at one end of my integral is 0. But it's not built into quad, evidently. It's not built in, which is okay. You just gotta, you can work around it. That's what your expertise is all about. So this is numeric integration. This is not symbolic. Symbolic is what you do in calculus with the symbols and everything. This just it chunks up the number line into bunches of chunks and figures areas based on trapezoids and stuff. Diff, let's see, let's give it a function x, or x equals, I'm just going to give it a range of values, 0, comma 1, comma 3, comma, I'm doing like a Fibonacci, good one is a Fibonacci sequence, 1, comma 2, comma 3, comma 2 plus 3 is 5, comma 3 plus 5 is 8, 5 plus 8 is 13, and so forth. That's a Fibonacci sequence. If I differentiate it, it will take the difference between the elements. So it'll start with 0, 1, 2, 2, 3, 5, and so forth. So 0 is the difference between these two. 1 is the difference between these two. 1 is the difference between these two. That's what diff does to a vector, to ordinary numbers, numerically. 2 is the difference between these two. 3 is the difference between these two. 5 is the difference between these two. And I did, let's see, 5 plus 8. Yeah, that's right. Okay. So that's how the diff function works. That's how the quad function works. Differential equations. So I have what's called a dp, which is so the derivative of p, dp out. The derivative, the idea is the derivative of p equals p. Well, what should that generate? If the derivative equals the function, what is that? So it'll solve the differential equation. It will not. It'll show t. Okay. So the way you call ODE3 is just an algorithm to solve differential equations. This is your independent variable here. This is your dependent variable. This is the function that creates the derivative. This is your range and your first guess. So let's just run this and see how that works. Yeah, it does generate the exponential function, and sure enough, it worked out that way. There we go, and we can pick out the variables now. Instead of x, I use p in the in MATLAB. So if I just type p, it'll show what p is. It's 36 numbers from near zero. Oops, where is it? There it is. From pretty near zero, and then it starts growing. And then, of course, t is just should be a linear space between 0 and 10. Oops. There we go. Divides up the interval. MATLAB decides how to divide up the interval, by the way, to get the most accuracy in this algorithm, ODE 23. ODE 23 just stands for ordinary differential equations, algorithm number 23. There's a bunch of other ones, too. Try this one first. Okay, you can do second order, which is a bit beyond this class, so I'm not gonna do it. I did another algorithm here. Here's a trick. Now this is what's called a global variable right here. That I've defined this variable, which this is a subfunction inside the main function, a nested function. We need it. Otherwise, I can't have basically, I cannot pass this variable into, the way this works, I can't have another variable in my argument list for the ordinary differential, for this thing here. I cannot have another variable in my argument list. It won't let me put this in here. But what I can do is create a bigger function here, and this function, this variable can be seen by the inner function. And when I do that, then everything can work out okay. Okay. So that's how you can use, this is one of those oddities about ODE 23, that I can't do it straightforward way. I got to go a roundabout way to get the work done. Okay, that's ordinary differential equations, and basically I just wanted to get to first order. For you guys, we've already talked about F0. Basically, we've covered chapter 5 too.